So I was just commenting that everyone is so quiet, and we still have a minute to go, basically. But everyone is ready to start, so let's start then.
Let's start. Yeah.
Okay, so we have Joachim.
Yes, Joachim. Yeah.
Joachim, he will talk to us about Egress Peering Engineering.
Correct.
And so we'll learn how to do more effective peering.
Yes.
There you go. So the floor is yours.
Cool. Thank you. And thank you everyone for having me here. So I will spend half an hour on talking a bit about Egress Peering Engineering. So there will be no DKNOG without a Cisco guy talking about segment routing. So I will do that as well. But I will try to keep it not too much into the protocols, not too much into the technology and so on. I want to talk more about the use cases. I want to talk a little bit about how SR is being deployed and how you can actually use it in your infrastructure. So Egress Peering Engineering. So why do we actually do that, and why do we need that? I would say a lot of things has over the years changed in the way we do our infrastructure, the way we build the internet. So as we all know, BGP is like, really old, back from the 80s. And the way BGP can create and do the peerings not really is sufficient to what we want to obtain. What we see is that the traffic is moving closer to the user, further out into the metro networks. It's a lot about the metro edge compute. I think many of you have heard about metro edge compute. The CDNs, they're moving further out in the network. And what we actually see is more than 80% of all the traffic we have on the internet is video. All that video is being generated somewhere. It's being generated, and a lot of it is coming from the CDNs, from the caches, and from the OTT players, right? Netflix, YouTube, and all of those guys. So normally or if you look a little back in the time, we had all these content providers. You reach those guys over the internet. So, but the demand on the traffic, the demand of how to be able to deliver this traffic has changed. So we see all these direct peerings we have with the content providers, direct peerings with the caches in the infrastructure. So all these changes into the infrastructure is changing also the way we need to build our network. So I think it's S&P, what they call Global Market Intelligence. They are saying that by 2020, 62% of all data will be computed at the edge. So that means we need to be able to have more traffic into the edge, and we need to be able to steer traffic to and from the edge. So I think most of you agree, if we run SP networks, that that this is what we are seeing, right? So we need to be able to steer our traffic much better. And we need to be able to do more peering engineering. And actually what we're seeing is we get a lot of weird requirements these days. People want to do all kinds of funky traffic engineering. People want to do things like disjointness. They want to do a latency-based routing. They maybe even want to do carbon routing, MACsec encrypted routing, whatever. All kinds of new engineering and optimizations are being put into the network as different requirements. So what we are going to focus on today is how to do this on the egress traffic. So you can do all kinds of engineering on the ingress traffic. You could do all kinds of engineering on the egress traffic. And what we want to do, focus on today is the egress traffic. How to do that. And what we want to obtain is we want to be able to live up to all these KPIs we have. We want to be able to utilize the network much better than we can do today. We want to drive down the cost, basically. So I guess most SPs has different kinds of peering points, different upstream providers, direct peerings, all of that, right? And you want to be able to completely be in control on how you deliver that traffic based on your KPIs and metrics. So that's what we want to address. And what we live with today is this really old protocol called BGP, right? The two napkin protocol, which we all call it, was like baked back, I think it was from 1989 or something. And it's, I would say, a little bit hard to manipulate and steer traffic just using BGP. We have these BGP path selection criteria that's been there for ages, and they don't really fulfill all the requirements we have to be able to manipulate our traffic. So if you look at the BGP path criteria, you can do quite a little actually. You can do things like local preference, and if people want to play with the METs, you can do that as well, right? But it's quite hard. But you can still do some tricks to do things like hot cold potato routing, but it's fairly limited actually. So what if you want to route your traffic with different behaviors depending on what specific PE you are and what specific prefix you want to reach? Latency, load on the links. Might be that you have a temporary congestion on your upstream, or direct peering, and you actually want to steer parts of your traffic to another egress point to reach the same prefix. It might be temporarily, just during a temporary congestion, right? Could also be like disjointness. We see things like banking industries. They say, yeah, we have two paths. We want to make sure that we always send this traffic from this data center out this egress peer, this upstream provider, and we want to make sure that you always send this peering link. We want to use this upstream provider. It's quite hard actually to obtain that with the BGP instruments that we have today. Yeah, and especially things like load sharing, also quite hard to do with BGP if you really want to look into that. And we want to also better control the traffic to and from our CDNs, which are consuming a lot of the traffic, right? So how do we do that? We do that with what we call Egress Peering Engineering. If we look back at the RFCs and the standardization forums, it's actually quite old. The concept was introduced back in 2014, where it was announced in, I would say, a session was in NANOG, I think, yeah. And then it became RFC in 2021. So I would say this is something that I would assume that all vendors are supporting today. So it's not like a Cisco specific thing, even though it's based on SR. And we are leveraging some concepts of the RFC 8402, which is generic segment routing standardization. We're using something which we call BGP peering segments. So yeah. Before I go into all these details about BGP peering segments, I would really like to know by raise of hands how many of you guys are actually running segment routing in your network or about to run it or do it somehow in a lab or something. So there is quite some. I know there is actually more than the hands I see. So so what we do here with SR is fundamentally we don't want to change anything on our BGP network design when we want to implement EPE. EPE functionality is something that's required only on the border routers, your ASBRs, as well as the EPE controller. And then when I'm saying controller, people tend to say, ooh, I don't want any controllers to do things, and it's kind of magic, what of this? But the controller function here is quite simple. You need what we call an SRPCE, a path computation element, And the SRPC is something that you enable on your any XR router. Basically, can do that. So it's a function you enable on your router, and you are actually ready to go. So the PCE controller is collecting topology information using BGP link state, and then it's actually also having the EPE informations, these BGP peering sets, as we call them, and with those kind of information, the SRPC is able to push out your policies based on your requirements. So I don't want to do SI in details, but I just want to give you a 1-minute recap of what it is, just to make sure everyone is on the same page, right? So SI is source routing. So what we do is that we push a stack of labels, could be SRv6 or SRMPLS. In this example here, I'm running SRMPLS. So we push a stack of labels to the header, to the ingress, on the ingress router, to the IP packet to actually do source routing and steer the traffic based on the labels. You have different label types. In brief, we have the prefix segment and the adjacency segment, where the prefix segment is something that identifies a node, and adjacency segments identifies a specific interface. And by imposing the label stack, you can fairly easy control your traffic on how you want to steer it through your network. And this is what we use for doing basic SR traffic engineering. And I mean, for those that haven't really enabled SR yet, definitely do it. It's super, super simple. As such, it doesn't impact anything. It's something you turn on your ISIS, and you you configure your prefix sets, and that's basically it. You're up and running, and it's hopefully shouldn't do any impact on your running network, so you can run it just turning it on and start using it. So what we do here with the BGP SR peering segments is we are adding 3 new types of sets. We call it the peer node set, peer adjacency set, and the peer set set. That's the only 3 things you need to remember. And those 3 sets we actually use to override the default forwarding behavior we have in BGP. So we want to overcome the limitations of what we are doing with the BGP best path selection algorithms. So the peer node set is always allocated. It's done dynamically. When you configure a BGP peer and eBGP peer, you allocate a BGP node set. And then if you have multiple interfaces links to that peer, let's say you're doing like an eBGP multi-hop session, you have multiple links, then you also allocate an adjacency link on a per link basis. So these peer node set means go to this specific peer, allows traffic to go out multiple interfaces towards this specific peer. The adjacency set, you can actually use that to steer the traffic on a specific link towards your peer. And then the last one is the peer set, where you can actually combine to have a multiple links or peers defined by a peer set. So with the combination of those 3 SR set types, you can do a lot of really cool traffic engineering. So as an example here, we have a reference topology. We have AS1, which is you. We are peering with AS4 and 5. One could be a upstream transit provider, one could be a local peer, whatever, and then to reach a prefix in AS6. So traditionally, we can't really do much. We can do like local preference and so on, but the BGP best path has chosen to send all the traffic out via router number 2 here, and all traffic will go through AS4. You might even have a congested link, so on. You'll start dropping packets. You can't do anything, right? You have to go manually and try to somehow overrule this, and it's really, really hard. Because you have a link through AS5 you could also use, but how will you do that? you're just dropping packets, right? You need to be able to steer some parts of the traffic to avoid dropping on that link. Might also be that the link to AS5 is maybe cheaper, better desired for some reason. In this example here, we have, we want to, I think I'm actually going to this one. Yeah, sorry. So the requirement here, we have enabled a SR. Very, very simple, router ASIs. We have a prefix SID allocated, so we have ASR running in AS1. So you can see we have the prefix SID with 16,003, which means if we want to send traffic to router 3, we just push that label 16,003 and it will go to that, right? You can see how that looks like here. If you do a trace route, you can see the labels being pushed and yeah, just fundamental segment routing. So what we now want to do is we want to enable this egress peering. The way you do it is it's quite simple. Underneath the neighbor, you just turn on egress engineering. Egress engineering will then start to allocate labels on those neighbors. So you will have the you can see here we have the peer node SID label 30,024, 30,035. And the example here, we also have multiple links between 2 and 5, but we have on those specific links, we also allocate the labels. So what can we do now? Now we are setting up the controller, or whatever we call it, is just the SRPCE. It's an instance you turn on in XR. The EPE controller here will then receive those labels, those SR labels, and we'll be able to use that for creating a policy you can push out. If you look at that controller, BGP link state, show BGP link state, you will actually see traditional BGP information here, where you will see AS number, you will see your local and remote node AS numbers, and what you will also see is that you are allocating this peer SID 30,025 towards your neighbor on router 5. So, really good. What can I now use this for? Say, okay, as we saw before, the BGP default behavior is to route from router 1 to router 2 and then to AS4. But there is this guy in AS6, this Mr. Important Network Engineer. He has a host address 61106/32. He knows that if going from router 1 to router 3 and then router 5, I get lower latency, or it's just a preferred path for him. So what we want to do is that we want to select that egress border router, and then we want to send it out that specific interface. That's really hard today. I mean, if you didn't have this capabilities, then how would you do that? You need to do really, really crafty source-based routing and stuff like that, right? So what we do here is we create a route policy. We set a next hop, we set the label, local preference, and that's something we are defining on the EP controller, on the PCE. So we are making this route policy. What we then do is we advertise this information to the ingress router. We do that with BGP label unicast, this example. It could be PSEP, it could be netconf, basically. You can do that different ways. In this example, we are using BGP plus label to actually get that policy pushed out. And what we then do here, if you go to router 1, we have the policy, want to send the traffic. He's then pushing 2 labels to the stack. The first one, 16,003, which is with the prefix SID to go to router 3. And then he's also pushing that label 30,035 to actually send it out that specific interface. Which means now that when you're on router 1, your traffic to that specific prefix 6116 will go out that egress interface. That's smart. So I hope you get it. So this is kind of the theoretical introduction. Now I want to talk a little bit more about some more use cases. What we can also do with EPE is we can combine this with traditional traffic engineering. So we can combine it with things like link utilization, traffic loss, latency, whatever. So it's not just about the egress interface and the EPE and the BGP peering sets. We can also combine it with other capabilities to do really fancy traffic engineering. If you have congestion somewhere in your network, you can do that. There is also the peer set. So what does this peer set do for us? So in this example here, we are actually having a peer set sit where we are having for the 10.00/24 prefix, we actually receive that from 3 ASs. What we do is we do a peer set sit on all 3 of those to actually do load balancing. So what we can do now here is we can push traffic. We're also combining it in this example with an anycast label. So of 17,001, which is owned by 2 routers. So our ingress traffic will now be perfectly load balanced across your network to your border router that will then also load balance the egress traffic towards all 3 peers. That's quite hard to accomplish without a technology like this. Really cool. What we can also do is we can do what we call weighted ECMP. So normally when we're sending traffic in our infrastructure, we're using like SPF, right? And SPF is choosing a path, and that's the path we're using, and all the traffic goes on the SPF path. But what if we want to actually have this traffic distributed non-unequal, so UCMP. In this example, what we are doing here is we make a policy. That policy is described by a binding set, as we call it, and then we can apply a weight. So in this example, we say, okay, I have my 2 upstream providers, actually 3 here, 2 of them, one of them has a bundle with a lot of capacity. I want to send 80% of the traffic to that upstream provider and 20% to the other upstream provider. And then the ingress router will actually be able to do that. So we haven't had that since EIGRP, I think. So it's quite nice. So we can actually also, with the SRPCE here, we can instruct the PCE. It has like a northbound interface, RESTful interface, where we can have additional, I would say, knowledge about the network as additional northbound controllers to interface to the PCE to actually change a policy while it's still there. So we can change if a link goes down between the on the bundle here between ISPA and router 5. If a link goes down, we can actually change the weight from 80-20 to, for instance, 60-40. So that kind of, let's say, controller functionality is not something that's built into the SRPCE. It's typically something you have on top, some kind of logic. That can be all kind of commercial controllers or something you do yourself or whatever. That's actually an example of that I have in the last slide here. It's a customer of ours that's building a fabric here where they are hosting caches. So it's a content provider, it's an OTT. So what they have done here is they have made their own controller. That controller is getting telemetry information about bandwidth utilization, response times, packet drops. That's going into the controller. And what they have done is those caches you see in the bottom, the 4 caches, they're actually running MPLS. They have an SR stack, which means they can impose any label and steer their traffic. So you can see they have X, Y, and Z. Those are direct peering they have with their partners. And then you have on the band interface A and B, they have like a traditional internet upstream, which is for them maybe not preferred, but it's there. And then let's say they are reaching the AAA/24 on X and Y, and you can see 93% of the traffic is going out router Y, and the 50% is only on router X. So they want to control that. And what we do here is we actually sell, you can see you have EPE labels 101 and 102. So you can actually, based on that destination, say, okay, I want to steer more of the traffic here on a specific interface and then out on a specific peering on router X to steer that traffic. So they are doing that directly from the caches. So they are, I would say, going a little bit further than traditionally on your MPLS infrastructure. And you can actually have a lot of information in that controller they're building. Telemetry data, all kinds of, they have IGP topology and so on in that controller. That was my last slide. So I hope you have some really good questions on EPE, and I hope we can have some discussions around implementing SR and how to move forward, because we really want some use cases. I can see Lasse, you have a question?
Yeah, Lasse from Telia. This is all for egress traffic only, and I don't have lots of that, so could you enlighten me? This BGP announcement from your peer, that then is your reachability to where you want to send the traffic. How is that reflected into your segment routing update, so you don't accidentally send this traffic through your segment routing SID to a peer where the BGP prefix has been withdrawn?
Okay, so I get it. So you feel, so it's to avoid like a disconnect of a prefix. So you actually end up sending, what you're afraid of is you're ending up sending traffic towards an egress interface of something which is not being announced by that specific peer, right?
Are you reinventing IGP?
That's what I'm hearing. Theoretically, you could do that. You could send any traffic to any peer by doing that, right? So for me, it's so when you apply the route policy, you have a what we call like a color and an endpoint in the SR policy, and if that policy does not match, you don't receive it, your BGP announcement, so you don't actually have that route available, then you don't apply that color and end policy, so if you don't announce it, if you don't receive it, you will not be able to tag the traffic, and you will not send it out that egress interface.
Okay,
yeah, we can discuss the details if you want afterwards. It's a little bit, I didn't have it here in the slides, so yeah, it takes more time to explain. No more questions?
Hi, I'm Nina. Nice presentation about an interesting technology about how to traffic engineer across your network. I got confused about your motivational slide because that one was about video being on the edge, and it doesn't really apply to this use case. The whole point of video being on the edge is that it's not traversing the transit networks, which is where this. So I'm just encouraging you to maybe change your motivational slide, because I think this is, if I was working at a transit network, I would love to play with this technology, but otherwise I don't really see the use case.
Okay. Yeah, but I would say it depends on whom you are. If you are the content provider, then it makes a lot of sense, as I see it, to avoid, like the last slide, to avoid sending traffic on your transit. You want to send it on your direct peer. And I would say,
yes, and they do that already.
They do that already, but they also have to
the point
steer
is,
it, right?
the video doesn't traverse the backbones, or that is what is being avoided as much as possible. This is a technology to choose the best path across the network, the backbone, but the point is to try and avoid it. That's fine. That's my feedback. You can take it or leave it.
Cool. Thank you. Thank you, Nina. Yeah.
Well, I would say we don't have any more questions, so we'll have the chocolate for you.
Oh, thank you.
You get a bigger one. And thank you very much.
Thank you.